There we go. Okay. Okay. Oops. This is what I was trying to. Okay, people. Okay, class, we're ready to get started. I'm Sudha Jamte, and this is the guest speaker series from the PathtAV class. So we are going to talk to a real AV engineer. I was teaching car cognition. I was teaching the technology of autonomous vehicle business yesterday. So car cognition is one piece, and then I had all these other, the tech stack and identity and the recent news of all the different car companies switching to delivery, what's involved in making that happen as a AV solution. So we covered a whole gamut of things, but specifically with car cognition is where the secret sauce is. If car cognition works, then it's an autonomous vehicle. Otherwise, it's just a vehicle, right? So I have one of my students from my past, and I'm going to let him introduce himself because I've been talking about him, bragging about him for a while. So I'm going to pass it on to Igor, and I'm going to go back into just, I'm going to switch off my video so you can hear Igor. Yeah.
Hello, guys. My name is Igor Tryndin. I currently work at NVIDIA Drive AV team, but please let's note that I do not represent the company. This is just like a private endeavor of talking to you.
Yeah, I've mentioned that every time I've shared about you this particular talk, I've said you bring so much experience in the space and you have perspective on this. So that's what you're going to share, and you're not representing NVIDIA. So that's
yeah. So let me give a little bit of introduction in terms of kind of like my technical expertise and my career in Silicon Valley. I came in here in 1997, just right out of college. So it's been 23 years already, give or take. And I worked in a number of technology companies in Silicon Valley. Like for about 10 years, I was doing kind of like a system programming, optimizations, making software runs really fast, some interesting project development like game development. So then for next 10 years, from like 2007 to 2017, I worked in digital imaging technology. I actually had my own startup. We were trying to do high dynamic range processing software, like using essentially, we were in a way trying to compete with like Adobe Photoshop, Adobe Lightroom, or like developing plugins for those applications. So I guess, my kind of like foundation of my knowledge is in digital imaging and in like visual processing. So, and then in 2017, I switched to autonomous vehicle industry. So I joined a group. I was still working at NVIDIA back then. So it was just an internal transfer. I joined a perception group, and last about like 3 years, I've been working on machine perception, machine vision problems.
And you took my AV bootcamp, the 2-day class, right?
That's correct. Yes. Yes, that was really interesting. I think no, it was called Business of AV.
Yeah. Autonomous Vehicle Business Intense Bootcamp or something we called it. Yeah. I actually specifically remember you because I used to teach this business of self-driving car as a semester-long course and made students do projects. So the first time I taught the bootcamp, I said, it's hard for you to come up with a solution and present in 2 days, but anybody who wants to volunteer, you get to present to the VCs at the end of second day. And you came up with a project and you said, for the fun of it, I'll do it. And I think it's some kind of road cleaning robot. Cleaning robot. Yeah.
Yeah, this was just a kind of, problem on the spot as I was driving to your class. I saw this like garbage lying around on the side of the road, and I thought, oh, let's create robots that will clean it.
Yep. Cool.
Okay, so how do we do this? Should I start presenting?
Yeah. So just in terms of logistics, let me see. I think I can give a view where you can see people. It's giving the speaker view, and I was thinking I can get a gallery view. I'm not able to get the. Okay, so people, do you see? So the best way for people to interact would be if you chat and ask your questions. And I'm assuming, Igor, you can tell me if this is okay, but people can just chat their questions while you're presenting. And if it is relevant, you can pick up an answer. Otherwise, you can answer in the end, and we can do that. Like, towards the end, you can go back.
Yeah, well, what I think will work best, you will moderate it. So just stop me and say, okay, somebody is asking question, because I'll probably won't be monitoring the chat window.
Okay. Okay. Thank you. Martin, thank you. Martin was confirming, yes. Okay, good. So there is going to be, and you, for all the students here, you can actually chat. I have some people who tend to, give references, or if you mention something, they would say, oh, here's the URL link and stuff. So feel free, okay? And then I will jump in if it makes sense. I'm going to try and listen in as much as possible because this is a very exciting topic for me. And I don't want to take the raise your hand thing. I'm not a fan of that. So just chat your questions away. Okay. So just for everybody else who joined a bit late, we are recording this, and you should have the archive of this back in the class section on driverless world school. And if you came from career pivots, then it's basically going to sit under the career pivots area for all of you. Okay. Yeah, we see your screen and you can get started, Igor. Thank you so much.
Okay. So again, good morning, everyone. So we're going to talk about data sets and in-car cognition. And I guess, cognition is not a usual term that's used in this industry. Typically, we use the term perception, like a machine perception, machine vision. Sometimes people say computer vision, but usually that refers to maybe more traditional, older techniques. But I guess, cognition would be a pretty good term to start using because it does involve a little bit more than just seeing things. It needs, the autonomous vehicle system needs to understand the world around it. And again, the context of this is we're going to talk about data sets, primarily focusing on AV data sets and camera, like a visual perception data sets, because this is my primary expertise. This is what I'm working on. I don't usually work with like other sensors like LiDARs. And again, this disclaimer, as we mentioned, I do not represent any company, and this is just my opinions and experiences, and only public information will be discussed. I cannot discuss any secrets, of course. So what we will cover. Again, I want to start from kind of like a very high-level overview of modern AI, because I think this is pretty interesting. We live in interesting times. A lot of happening in this world, in the development. Sometimes, it's even hard to keep track, even for for an insider like me. Things happening so fast, and so many new technologies and kind of models and achievements are generated pretty much every day. So it's really amazing what's happening right now. This technology is solving problems that were thought to be unsolvable for like decades. And we have this kind of like a breakthrough that happened like about 10 years ago, around like 2010, 2011, where kind of things that I mean, AI is not a very new. People worked with neural networks kind of, I don't know, in 70s and 80s, and a lot of things were invented in the 90s. But what gave it a boost, this technology capabilities that enabled execution this at kind of reasonable times, being able to run it at real time. So, this is what we will look at. And we're going to talk about data sets, particularly like a scale of data sets, how we how they created and managed, and talk about in-car cognition, more, more like perception. And I want to consider a few corner cases because I think those are interesting. And I think this also kind of challenges people to think about it. How do we solve this? How do we actually make machine to kind of make intelligent decisions, kind of have this cognition we're talking about, and like behave like humans, or let's say like best of human drivers in autonomous vehicle technology. And again, as I mentioned, this is going to be mostly focused on visual perception, on processing camera inputs. I will mention some other sensors in the context of this, but I primarily work with cameras because this is probably like the most interesting sensor, the most kind of data-rich sensor in terms of the amount of data, the amount of information it can sense and input into the system. And of course, we all know about human vision. Our eyes, the human vision is the primary sense. Blind people cannot see the world, and this is probably like the most information that we as humans receive about the world. So this is what's the most interesting in the AV world as well. So I don't know how many people remember this, going back to the advent of computers and kind of like programming. There was this mantra or like a formula. I think it was introduced by this guy, Nicholas Wirth. He's like, one of the pioneers in the 70s. And he said programs equals algorithm plus data structures. So back in the day, this was kind of like a mantra, how you develop software, right? So in our days, we're talking about AIs, we're talking about all these wonderful things, and AIs is also this kind of like a formula, data sets plus models, or models plus data sets, So you have AI models, which is just a description of a structure of a neural network. And then you have data, which is probably more interesting and plays kind of bigger role here, but model is important as well. And you train your model on this data. There's a specific technique how it's done, and then like magically, suddenly it you feed it new data, and it just works as as good as on training data. So like I think the term is used is that the model generalizes on like data that has not been seen during the training. And there are many techniques and many kind of approaches that are used. In particular to autonomous vehicle world, I think there are like a few techniques that has become common and have proven to be working pretty well. For example, when we talk about object detection, typically something called YOLO, it's translated you look only once, type of approach works really well. And essentially what it does, like in this picture, it gives a bounding box. So it gives a location of the object as well as its class. So it classifies, pixels inside that location. And this is done in one pass. So there's no like kind of multi-pass algorithms. The network the neural network just takes the image and outputs this data structure that allows us to understand, okay, this rectangle of pixels actually represent a car. This rectangle of pixels represent a bicycle. So this is like one common approach to do this. Sometimes they call it bounding box detector. That's also a common term. Another common approach is something called semantic segmentation, when we try to classify every pixel in the image to belong to a certain class of objects. So like in this case, so we can segment, the road surface, we can segment the cars, we can segment maybe like a traffic light, trees, some background, maybe some like other structures, pedestrians. So this also helpful in like understanding the environment, understanding this visual input. So, and in terms of the actual models, I guess, as I mentioned, there are many approaches that are used in the industry, used in the autonomous vehicle world. But a common approach is use what's known as a convolutional neural networks, and essentially this is just like multi-layered architecture of you start from input layers, you have a bunch of hidden layers, and then you have output layers that actually does what it needs to do, outputs like this kind of classified and structured information about the picture. And one way to think about the architecture of the model, how this is done, which, for example, I commonly do, and I guess many companies do, is that you can think about it as a kind of like a combination of different blocks that achieve a specific purpose. Basically, like I, as an engineer, when I looked at a problem, when I need to maybe come up with some new subsystem in the car that does a specific perception function, I would just take those blocks and combine them together, and then just kind of go with that model and see if it works. Sometimes there's a procedure called neural architecture search, when we try to figure out most optimal parameters of that architecture. I think people use this term hyperparameters. So this is describing kind of like the size of layers, like how many like layers at each block, and so on. So there's like a many kind of techniques, and I'm not going to go in details here. This is again, this is about data, not about AI models. So
this is actually good because this path to AV is 2 courses. So there is the AV masterclass, which is equivalent of the bootcamp that you took. And then there is the business of AV data, where we actually go into connected and autonomous vehicle data. So we looked at different data sets in the last class. And so the semantic segmentation that you showed, we went through what does that mean in terms of, labeling the data. We didn't look at the algorithm models. So if this is the right time, I have a question.
yeah, go ahead.
What drove the need from going from YOLO to, a whole CNN model? What is the gap that is driving the industry perception space in general, saying, okay, we need new models, we need to improve? Is it trying to fill in for some specific optimization, or is there a general standard problem set in the industry that everybody's running towards?
Well, I think this is a general approach that drives towards like new models, and the driving force, or like like what makes it advance, is that we need improvement in performance. We need well, first of all, there's just 2 things here. We need to be able to run it at high performance in terms of like accuracy of detection, being right about things.
Yeah.
We don't want to run into situations when we have something in the car and it doesn't notice, like some, I don't know, a pedestrian walking across the road, right? So we need to improve the performance in terms of the accuracy. And we also need to improve the compute performance. That's also pretty important, because you want to run those models in real time. You don't want to like input an image and 2 seconds later you get the result. It's just not going to work. It's not practical. So you need to be able to run, I don't know, dozens of those networks, of those neural networks that doing different cognition functions, and like do it, I don't know, 30 times a second at a frame rate. Typically cameras work at like 30 frames a second. That's like 33 milliseconds per each processing cycle. That's extremely fast, and this is like a pushing the limits of compute capabilities of the platform. So if we can optimize, if we can find a more efficient architecture that allows us to achieve high accuracy at the same time, being able to run it in real time, that's our that's our solution. That's what we go for. That's what drives this research.
So there's a question from Hani. Hani is actually my past student from an AIX class, which is about designing AI in the car. Joining us from Dubai. So he's familiar with AI very well. So he's asking, does that mean the car is going to be filled with GPUs in in the future. And he says GPUs on wheels.
Well, it's already filled the GPUs. So come check out what NVIDIA is doing. It's called Drive AV platform. There's a pretty interesting page on NVIDIA website called Drive Labs that's mostly presents the work of my team, like a perception team. There are many interesting videos. So we have this lady who's from marketing, Neda, and she's usually presenting it in a very kind of well-explained fashion. So come check it out. So let's continue with the presentation.
Yep.
Okay, so let's talk more about data sets, because I think this is the most interesting, the kind of more critical part in all of this. And for visual data sets, we typically talk about image plus labels. So we annotate, and again, this is an approach that's called supervised learning. So the AI is learning, is trained on data that is known as ground truth. So this is created by human operators. So this is annotated, and for example, in case of bounding box detector, you'll have an image, and the operator will label every object in that image, and like draw the bounding box around it, and that information will be used to train the model. And you need like a lot of data. We'll look at the scale of this. So like a first layer of this is, of course, getting label data, getting annotated data. And this is, again, something that we'll talk about, the challenges. So then another technique that will be used here is something called augmentation. And we're trying to kind of come up with like create a variance, small variance in the data by augmenting it. Again, I'll talk a little bit more about it later. So then in our approach, that we call the auto labeling. So essentially, this is when we can utilize other sensors data to create this ground truth in regard to the image, and then train the visual detector on the auto label data so that it has a certain capabilities. And then, of course, another quite interesting area that's, I think we're going to see a lot of development in the next, I don't know, couple of years, is when we talk about simulation and using fully synthetic data. And again, I'll talk about this in the next slides. So let's look at scale of data sets, because I think this is kind of important in the context when we talk about what's available publicly, like the data sets that are released by other companies, but by AV development companies. And I like to look at this as kind of like a 3 levels. And going from one level to another is about 10x increase in scale. So I think most data sets that you can find online or like available, just come and grab it, experiment with this. This is kind of like this first layer when the companies, of course, they're doing it for kind of like educational purposes, for like, this initial research or like a proof of concept purposes, so that people, engineers, students in this technology, in this area, they can just come and grab and just, go and experiment with this. When kind of coming to the next level, when more serious stuff start to happen, inside the companies, we increase the scale of data sets to about 10x, and we're talking about 100K up to 1 million size of the data sets that are used in research and development, maybe various experimentation, kind of like solidifying this technology. But what's more interesting is that transitioning to the next level, when you want to go to production, actually requires your data set to grow even more, even like, this in our step in 10x magnitude. And I think this is what makes this technology, this development is pretty challenging, especially for small companies, because kind of like producing this type of data sets and managing them becomes pretty kind of serious endeavor. It requires a lot of resources, a lot of time and money, and we're going to look at this. So let's just look at the cost of this and kind of like, what's required in terms of money and time. About 2 years ago, I was actually seriously considering starting my own company in simulation space. And I looked at kind of like various offerings when like data annotation companies. You can actually create a business by doing this data annotation. That's, I guess, pretty much in demand right now when everybody is trying to do this stuff. And so I kind of got this quote, like $5 to $8 per image when these companies offer their services. And imagine that you need to create a data set of 1 million images, so that becomes quite costly. So you're looking at like $5 million of cost. And if you look, that's not only like the cost, it's also time that's involved here. If you think about, maybe a labeler spends, I don't know, about 10 minutes per image, because it needs to be thorough. It needs to like notice all the small objects. Sometimes there are a lot of information in an image, so like maybe 10 minutes per image on average. Some images take longer, some images take faster. So maybe 40-50 images per day. Essentially 1 million data set will require 20,000 labeler a day. Basically, if you have a team of 100 labelers, it means you will be able to do it in 200 work days. That's like you're looking at probably about a year of actually delivering this. And imagine this is like 100 people, so you need to manage them. Another problem that will happen with people is that there's going to be some errors in those annotations. Typically, I think it's known to be about 2 or 3% of um, error rate, so that like images that or annotations that would have some sort of issue, some sort of a problem. So you would need to do like audit of this, sometimes like multiple passes. So it's like this annotation and labeling infrastructure becomes a problem in itself. And then imagine that you also need to do it per multiple cameras, because you want to have a surround perception. So you want to have like, front-facing camera, you want to have a side-facing cameras, multiple cameras, you want to have a rear-facing camera. And then anything that's changing sometimes may require like recapture and relabel, again, kind of going again for this experience that's very expensive and very time-consuming. So this is not an easy task to achieve. This is very expensive, and this is why, for example, when I hear about like a startup of, I don't know, 5 people that have, I don't know, $10 million investment, and they come out and they say, oh, we're going to build an autonomous vehicle and we're going to solve all these problems. I kind of a little bit skeptical, because they're just at this amount of resource and at this investment level, that's probably like not even feasible to achieve unless there's some sort of like a major breakthrough in how this is done. So then again, when we talk about this size,
there is a question. There's a question from Emmanuel. Right. So do you think that the current computer processing speed is the bottleneck for AV? Do you think that a new computer hardware and architecture will have to change in order for the AV data to be in full production?
I mean, it is a bottleneck for kind of trying to do more and achieve more. It's always, I mean, sort of like this technology, this development, it always pushes the capabilities of hardware, of compute, like a capacity of compute. And I'll give you an example. Again, like NVIDIA, maybe 2 or 3 years ago, it announced this new platform called Xavier that was supposed to have 30 TOPS. It's like 1 trillion operations per second. Again, this is kind of like a rough metric to measure it, to measure the compute, but this is kind of common, right? And right now, our next generation, I believe it's announced to be 200 TOPS. So this is like 7 times increase. And this is just sort of like a realization that, something that people think about would be sufficient 3 years ago. Nowadays, everybody realizes, no, it's not going to work, in order to kind of be able to kind of churn so much data, churn so much information, and do so many things. We'll look at this later, like all the subsystems that need to exist in an autonomous vehicle. This really needs to like tremendous compute capacity. I think like other companies, was it like a Qualcomm announcement? They said they're gonna do their platform with 700 tops. So that's even going further in terms of the compute. How much compute will be enough? I mean, it's kind of hard to tell at this time. It's still, in very active development, and I think again, this always be kind of like these algorithms, these approaches, uh, always gonna push these limits of how much compute we require, and like in the future we may desire to do even more things and kind of put a even higher requirement on the compute. That's just the nature of these things.
Okay. So there are companies who are doing, when you were talking about this whole cost of getting annotated data, right? There are companies which are outsourcing and saying, okay, we can have a human annotated, or there is this whole mixed model, right? That you actually use an AI to actually triangulate and validate the labeling itself. And there are
Correct. Yes, correct. I'll talk about this in a little bit more detail on the next slides. So then another challenge that a company that's developing will face is sort of like managing the size of this data. So for example, if you look at HD size, this is a 2 megapixel. And typically we look at like a 16-bit channel because we want HDR data. This is like a FP16 representation in a floating point, like half standard floating point. So you're looking at like 12 meg per picture. 1 million data set pushes this into 12 terabytes. If you look at 8 megapixel images, that's 4 times more. So 1 million data set pushes it into 48 terabytes in uncompressed form. And then this is multiplied by number of cameras, number of detector subsystems. So you're looking at probably like a petabyte level, or like a multiple of petabytes of like data that you need to manage efficiently, kind of get in time, for your trainers when you train your networks. So this is not a kind of very easy feat. This is like a pretty serious problem, kind of building this platform, this efficient data management platform. And this is what, for example, companies like NVIDIA is doing. They're realizing that this is where value will be, that we need to build this platform that delivers these capabilities. And kind of like talking about the size of this, we can introduce compression, which is typically gives us about 10x reduction in size, but that still, again, has its own challenge because data need to be uncompressed at a time for training. So there's like a kind of different things that have to be kept in mind here. But the main point here is that data management platform, AI infrastructure platform enables this. And without this efficient data management, it's just not going to go too far. So I mentioned, and so that you said about this, like additional techniques that let us manage this in a more kind of practical manner. So I mentioned these techniques. One of them is known augmentation of the data. So basically, when you create some data set and you can create more data by augmenting existing ones. And typically we talk about something as simple as kind of scaling, rotating, kind of flipping images, or doing like tweaking on color and exposure. So you introduce some variations in this data, but you keep the existing labels so that that, for example, location of a car in the picture doesn't change, or like if you say like you rotate it or you flip it, how it's changing. And then you can automatically create much more data than your original human annotated data set has, and use it for training. And that approach works quite well. And another interesting technique that's used here is if you know about this term called GAN, it's like a generative adversarial network. So this is like an approach of creating this AI when you can take existing picture or take some existing kind of image and turn it into something else. I think the most famous example of this is when this is called like a neural arc. When you take a regular picture of say like a person and you turn it like into a painting of a famous master and famous artist using like this style, like maybe like very abstract style. Those approaches can also be used to do like a pretty cool things when you take an image, let's say it's a daytime image and you can actually turn it into nighttime image. But of course, because you know this metadata doesn't change, like cars remain in their positions. So now you can you can extend your data set by creating like, more nighttime images or doing like, vice versa, creating like a twilight conditions, kind of doing all these different variations and kind of blow up the size of your data set quite significantly. And again, this is all happens in automatic manner. So like humans are not involved. This is like, very fast and very efficient. And also, do things like, change weather, for example, turn like a clear weather into rain or like snow or like a foggy, change like a season. For example, it's summer, you can turn it into a winter time, have like snow on the ground, and so on and so on. So this is also a pretty powerful technique of augmenting the data by GANs. And the next one is...
So my question was, like there are companies like 8x8, this whole business is just labeling the data, the annotation piece, right?
Correct, yes.
There are set of companies who are basically saying, we don't do this using a human, we are using some kind of GAN technique to even annotate or label the data.
Mm-hmm. Yeah. I mean, humans will have to be involved because it has to be supervised to some degree. You just need to make sure that it's doing the right thing and it's not missing, like, for example, some objects. It can become quite efficient. And I guess, like the companies, they do realize this challenge of creating this huge, vast scale of data sets that it's just not practical to say have a price tag of $5 million on your data sets. It's just like not going to work. So you need to reduce this price, and like all these different techniques can be used. And this is a business opportunity because if you can do it faster and you can do it at a lower cost, you win business of those companies. That's just pretty clear.
So Hani has a comment saying, I guess that's why there are partnerships in the industry to create ready solutions for AI with the right component of compute storage.
Correct, yes.
Yeah. I have another class called AI Bootcamp, similar to the AV Bootcamp, where we basically, talk about how you get the model from, one set of tech companies. And then as an industry person, you look at what data you have in your business, and then how do you kind of do the modeling. So just wanted to put that for the class because I see some of those students here too.
Okay. So then the last technique of augmentation is when you can create synthetic objects and insert them into the picture. That's also pretty useful because that allows you to introduce kind of variance in your data set for things that may be hard to encounter in the real world. Like one thing I'll talk later about, like one of the detectors in the car is centered around detecting road debris. So imagine like your AV goes on a road and there's some, like, I don't know, somebody lost a couch, was transporting a couch and it's like in the middle of the road. And obviously that's something that's gonna maybe be hard to encounter in a real world, but those things do happen. So like one technique is that augment, you actually like synthesize those objects, like 3D graphics is pretty advanced these days, and you insert them into the picture, in the right position, and then you can train your models to recognize those debris, or like any other type of, I don't know, you can imagine, let's say like a wild animal kind of runs from the forest onto the road, and then there can be like a different type of animals. That's going to be pretty hard to encounter during your data collection.
Moose,
Yeah.
honey's moose detection. Yeah.
Yeah, exactly. But maybe it's some sort of like a rabbit that comes, runs. And so this is where like a synthetic objects can be pretty useful, just utilizing the capabilities of 3D graphics, like, advanced in rendering, and just augment your data sets by those objects. Then the next technique I mentioned is something that we called auto-labeling. And typically this involves kind of using cross sensor information. So when a data collection car goes out into the world and actually records the data, it doesn't only record the cameras. It can have, for example, it can have LiDARs. That's pretty typical, and LiDARs will measure, will give you this thing called a point cloud that will give you a distance to each point in the image. Or you can just record things like inertial measurement units, so sort of like the motion of the car, so you can know how the the pose of the car is changing, and as it moves forward. You can record things like GPS. I don't know what else. Maybe some like, again, different type of maybe there's like a 3D camera that uses like there's this technique called the time of flight, when it's not like a LiDAR, but it sends pulses of a specific wavelengths of light, and then measures like the time it takes to reach back. It's called the time of flight camera. So maybe like a less traditional sensor. Anyway, the car can be equipped with many sensors, and they record this data, and the kind of major thing here is that those recordings happen kind of synchronized. So that when you see an image, at the same time the car changed the pose in a specific way, and those that sensor data you can cross-reference, you can fuse it, and that comes pretty useful, especially when you try to extend your data set. Let's say in this case, an example can be, let's say you have an image detector, so you have an image, and then you annotated this, but at the same time you have a LiDAR recording, so you can actually take each point in your, let's say, bounding box, and know the distance to it. So you can say, oh, I know that car was I don't know, 50 meters away, and that information can be a label in your image, and you can train your network, your neural network, on that distance data. And now your neural network can predict the distance from just an image. So basically, it's sort of like you use the LiDAR during the data capture, but for your production, you don't have to have a LiDAR, because LiDARs are pretty expensive, so like $50,000 for a unit. There was like a bucket kind of type of device that like Google cars have, or some other cars have. They're quite expensive. Like if you move that distance detection capability just based on image, just based on inexpensive camera, that's a lot of a lot of advantage in terms of the cost of your solution. So then, you can use like capture car ego motion, kind of reconstruct the motion of the car. And because it's a recording, you can know how the motion will be extended into the future from a current moment, if you're considering. And for example, this technique can allow you to reconstruct the shape of the road ahead, because, the car will move in the next 5 minutes, ahead, and then, it'll change the position in a way that how you record it. So like if you're from the current vantage point, like in the moment of the past, relative to this future that you recorded, you can actually reconstruct the shape of the road, or like a shape of your trajectory, and also train your neural networks on that data, and that's also comes pretty useful. Or like another probably like technique. Let's say you record a motion, you look for a specific motion pattern. So like the car slows down, stops, and I don't know, waits like a second, and then goes. You can kind of assume maybe this is when we were going through stop sign intersections, because this pattern is maybe like quite recognizable, quite distinct in the data. So you can sort of like say, okay, I can automatically extract from my recordings the situations when we were going through stop sign intersections, and use that in a specific neural network that does that type of detection. And the beauty of this is that this can all be done on a massive scale without using human labelers. So you can produce like kind of very large data sets using like a cross-referencing the different sensor data and label them, and then like use it for training.
So this whole car motion pattern detection is fascinating. I've heard of this in the IoT world of tracking people's gait to see how they're walking and stuff like that. I did not know that was done in the AV space. Is that a standard data set that's available outside? I've typically seen only the 2D, 3D model, point and cloud, or camera images when companies are putting out public data set from Waymo or Argo or Aptiv. All of them are just pure computer vision images, right? Is that
that's
is
interesting
that a
question.
startup thing? Is that unique to NVIDIA maybe, or is that an industry standard data set?
In terms of sort of like a cross sensor data use, again, I actually don't know whether such data set exists. I'd imagine it's not that hard to produce, because things like IMUs, they're not very expensive. This is like, you can get like a decent sensor for like under $100 and kind of like install it and record it.
Yeah.
So like, I'll have to look. I honestly, I don't know if there's an existing data set, but this is kind of like a pretty obvious technique to use this like other sensors data to kind of complement each other.
No, I've heard of, just, validating the ground truth from multiple other sensors other than camera. But I didn't know about the car motion pattern. So I'm curious if there is a public data set. Like you said, it's easy to train just a model on that, to understand that, beyond the augmentation piece. So I was just curious if there's an external data set. So thank you.
I don't know, like this is, most likely there is one, and we'll just need to look. Okay, and then we mentioned about synthetic data. I think this is a pretty interesting area of development, and a lot of companies have invested a lot of resource in this. This is what's being built. NVIDIA is building its own platform called Constellation. Like, imagine like a large data farm that is able to do like very, very detailed simulation, very detailed like models and physics, like interaction of objects in the scene, and then actually extract the data, because the beauty of this is that like kind of annotation of this data can be pretty much like automated from start to end. There's no human involved, because you just create an algorithm that extract, okay, you have a pedestrian, it's kind of like a bounce, because this is a model in 3D, and then you can just project it into the image, and then this is just a label that just comes and can be generated on massive amount of data without that like a human annotation part, right? And so current graphics, I think it can do pretty amazing capabilities in terms of like doing ray tracing in real time, doing like various material modeling. Again, kudos to my company, NVIDIA, that released this ray tracing capabilities. Like, for example, this image that I included, there's this data simulation company called Applied Intuition. I know them pretty well. And so they going in this like photorealistic simulation, and they're producing these data sets using those approaches. Still,
one of my students works in LG, and LG has a simulator that they put it out in open source. So if people who are already from a past class, you can find Steve Lemke in the Slack channel.
Yeah. Again, there are many simulators, but I find that most of them are pretty limited, or kind of they're like pretty I don't know,
Rudimentary.
simple, yeah, rudimentary games, because it's actually not very hard to sort of like take some game design engine, throw in some models, and then quickly kind of apply some simple physics simulation, and then like have a simulator. But what I'm trying to say is that there's still a significant gaps that exist to achieve a full physical sensor simulation, and this is where I think a lot of interesting development will happen in the next few years. Is that companies will push this kind of frontier of going into like a fully simulated physical reality, which is pretty hard to do, and achieving what I call a sensor realistic simulation, so that the data that you get from simulation, like from these sensors, they will probably be pretty much indistinguishable from real data. So basically, you will look at a picture and you will not be able to tell whether it was captured by a real car or it was simulated, because those type of capabilities already demonstrated in 3D graphics. But for sensors, it requires maybe going into like more details of kind of physical aspects of say like if it's a camera, you need to simulate the phenomena that happen in the lens, like different kind of like refraction, different type of um, like distortion, as well as like filters that are kind of exist in the optical path of the camera, like simulating the sensor itself. And that way, you can close this gap, and you can essentially achieve when you don't need a actual data capture in the real world, which would be ideal. Because imagine that you can do things like, I don't know, simulate accidents, right? Obviously, like you will not do it in the real world where you will have like real people participate in that in the accident. You don't want to hurt anybody, right? But you can do this type of thing easily in a simulation when you have models of people, you have models of cars, and then imagine like you introduce some like a bad actor in the scene, that guys, I don't know, that just looks like a drunk driver, and it starts like hitting people or start driving erratically. So like, and then you want to see, okay, how my AV design, how my AV system responds to that. Obviously you will not be able to do it in the real world. And this is where the benefits, the like tremendous advantage of simulation will come and play, and like deliver this advantage, so that you can simulate things that are not practical in the real world. So I guess I'll try to move faster because there's a few more examples. And how much time do we have, Sudha?
So we typically finish by 10 o'clock, but we can go for another 10 more minutes if you want.
Okay. I'll try to move forward a little bit faster. So then, we talk about data sets, and then, you also need to understand the scale of sort of like a different AV perception systems that need to exist in your AV solution that does these different perception functions. And I tried to list some of that I kind of just come to my mind, and I know that just sort of like a necessary in a real EV system. So like you need to understand lanes and 3D structure of the road, like how it's shaped, ahead of you. You need to understand and recognize intersections, things like crosswalk, maybe, I don't know, railroad crossings, stuff like that. That's like a different type of kind of perception task. You need to see road markings, obviously traffic lights, understand, whether it's a red light, green light, and kind of different challenges come in that. You have to do road sign detection, kind of like a different announcement board that you can see on highways. Like even people talking, when they talk about this, like road sign detection, they're talking about having capabilities to do OCR. So basically OCR is when you actually can understand the what's written on the board, because it can change, because you cannot train for like your AI with some static kind of messages. Those messages can mean a different thing in the future. So the car need to recognize it. Things like path trajectory for motion planning, You need to do, of course, obviously dynamic object detections. That's like other cars, pedestrians, maybe we talked about like wild animals or any type of things that can move. Um, it also needs to do state estimation, like we need to understand, how fast things moving, what direction, whether they accelerate, all the parameters. We need to do distance estimation, track objects and predictors future state. And object tracking is also important when you deal with things like occlusion. Imagine that you see something and then it gets occluded by like let's say it's a car that gets behind a larger bus. You still need to track it. You still need to know that it's behind that bus, so that when it comes out from it from behind of it, you prepare it. You know that object is there. So then again, drivable space and obstacle, that's very important. We will look at one example of this. Landscape features, that's usually used for things like localization, localizing yourself within the environment. Vehicle signals like brake lights, turn signals, like hazard lights, street lighting, again, maybe during nighttime you don't see a lot, so that you can recognize street lamps by seeing them illuminated. That's like a different type of challenge. Like a road special lighting, when you go through like construction zones or accident zones, they have a special lighting. Then of course, you need to understand whether the road in front of you is kind of flat, or it doesn't have like bumps, or it does have them, so you need to adjust. We kind of mentioned about um, detecting road debris. That's pretty important. And then of course, in the end of it, you need to go and park, so you need to detect parking spaces, work in parking lots. That's pretty important. So kind of looking at the scale of it, imagine that each one of these require like a million images data set, and then some of these subsystems require multiple cameras. So this is where you can kind of understand and appreciate the or like be awed at the scale of this. When you're building this system, that's just a lot of data that you need to have a practical solution, to have a production level solution. So, we come to talk about this part that I think AV cognition is a good term. When you have all these different perception functions that detect different things that can happen and exist in the environment, and detected in in different conditions, day, night, different weather, kind of again facing different challenges. And all the data, it comes, you developed it. Now you need to kind of combine them together. You need to cross-reference. You need to fuse it together. And there are different techniques that can exist. And I think about it as that maybe there could be an architecture that talks about this sort of like a bigger AI that works with these different kind of senses of the car, that combines them together and present it as this common cognition function, resulting in this surround world model, which is a 3D model that has an accurate state of all the things that move around you, and also predicts what will happen in the future, because that's pretty important for planning. And this is sort of like I see this is what can be called AV cognition, that sort of like a step up from the perception function. And in a lot of cases, if you kind of look at the existing art, companies use what's known as a traditional algorithms, sort of like a filtering techniques, kind of like a different data structure that track those objects, or represent the world model. But I think in the future, that we will see is that what will be required is that this sort of like more of AI coming in and taking this role of like a higher cognition function to solve these problems. And the example of these problems can be we need to assign objects to lanes. So when you have a car in a distance, and maybe it's like a 2-lane road, you need to understand, oh, is it in my lane or it's a different lane? Because if it's in my lane and I need to adjust, I need to maybe adjust my speed. If it's in a different lane and it's not trying to merge into my lane, even though it's in a far distance, okay, I don't have to do anything. I can just dismiss it at that time. Do like different type of associations, or do like different like a planning trajectory computes depending on what you see. So again, like this is where this cognition function will come and play, and maybe more advanced techniques like a step up from a perception function will be pretty important. So let's talk about some corner cases. We need to wrap up pretty quickly, I guess. This is something that happened just a few days ago. We have this heat wave here in California, and a power outage was in my neighborhood. So, lights were out. So traffic lights on the road were not working, and the police came in and installed these temporary stop signs. Basically, I think the law says that, when you see a temporary stop sign at an intersection, that sort of like overrides the traffic light, because it's just sort of like logical, right? So that maybe this is what we want people to do, is to stop and treat it as a stop sign intersection. But when the power came back, the traffic lights started to work again. So you have like green red light switching, and then you have a stop sign that was not removed. Like police hasn't come yet and removed it, and you create this like a confusion at this intersection. Like a lot of people just look at the traffic light, they don't even notice the stop sign, or they notice like too late and they start like a braking, like kind of trying to decide to stop instead of like going through the green light. So it creates like a lot of kind of disarray, disorder around that type of intersection. And this has kind of introduced interesting challenges for behavior of autonomous vehicle when this situation is encountered. What should an autonomous vehicle do? For example, let's say it's a green light and cars don't notice that temporary stop signs. Should we follow the law, or should we follow sort of like what I call a group behavior? People behaving a certain way, and then like kind of, okay, it's a green light, nobody's stopping, I don't stop as well. Or sort of like, no, I need to follow the law and I need to stop, but by doing that, I'm actually creating this disorder, because other people will not expect me to do that, because they expect me to go through because it's a green light intersection. So this is like an example where it's kind of like a controversial, just given like this temporary stop sign or temporary road sign, or like a traffic control device that's installed, and that kind of contradicts what the other traffic control device is saying, or like this green light is displaying. So it's an interesting question. Again, kind of like I think about it, like how should we design our AV? Should we follow the law, or should we follow like kind of look at the behavior of other people and follow what those other drivers are doing? That's an interesting dilemma.
So this is going to be something that is baked inside each AV, right? So each company who's actually building the AV is actually thinking for corner cases like that. So we came with this whole concept that AI is making all the decisions, and it's not a program logic by the programmer, but now you're bringing in a program logic. Is that right?
Well, I don't necessarily mean this is a programmed logic, but I mean there is some sort of it doesn't have to be like sort of like a very strict that, okay, I see a temporary stop sign, I have to stop because that's what the law says. Because as we can see, kind of like a following that behavior, although this is kind of like a law abiding, this is what's supposed to happen, but following that behavior can make this less safe, because you sort of like breaking the patterns of like other drivers, other people passing through that intersection, and that makes it more dangerous. So like in this case, the car may decide, okay, I will go with my choice will be to make it more safe, and I'll just follow like the other cars that passing through the green light, ignore the stop sign. And that's totally possible. This is how it'll be done in the future. But again, I'm just asking the question here. I don't think there's a lot of solution in this regard in terms of how this is going to be handled at this time. this is sort of like a debate for the society, what should an autonomous vehicle do? Should it be like, very law abiding? Should it follow the laws strictly, or should it sort of like bend it a little depending on the situation? Another example can be people going on a freeway and there's a 65 miles speed limit, and you know that nobody follows that. And this is actually like a car that goes at 65. Usually that's just like a slow car, and other drivers start to sort of like tailgate it, cut it, or like, honk at it, be kind of upset at it. If everybody moves at like, 70, 75. So essentially, like a better, like a more safe solution would be to go with flow of the traffic, actually breaking the speed limit, but making it safe. And again, this is sort of like a question open for the society. What should be acceptable here? How should we design these things?
So Hani is saying that the car needs to behave like a confused human being. You have to simulate that.
Yeah, I mean, that's an interesting question. So anyway, let's look at this example, because I think this is pretty interesting. And I don't know if you've seen this. Let's see if I can do this. If you've seen this post, right here. So basically, what happened here is this is a recording from a Tesla autopilot, and there's this place on Highway 101. This is like one of the major freeways in Bay Area here in California. I mean, this is like where headquarters of Tesla and their production factory is located. So you imagine that this location has a lot of Teslas going around and in this autopilot mode. So this was recorded by one of the Tesla users, and what happens is that this is not like pretty easily seen in this front camera capture, but you have regular lane markings, and it's like a pretty low contrast on this image that kind of tells that probably Tesla is not doing pretty good job on processing the image in these conditions, because you have kind of like a challenge of sun shining into your camera and like blinding it and creating this haze and like reducing the contrast. So this yellow line is almost invisible. And what happens is that here you can see there's like this old lane markings that's kind of shifted to the left, and the car essentially, like you see, it kind of like nudged it. So it tried to take that old lane, and then you have this this construction barrier that's coming up in front of it, and essentially it just drives into that construction. So the guy at the wheel has to override, has to like kind of I don't want to run into this. I don't want to total my car. And I think he mentions in the comments that these new lines, new markings makes autopilot dangerous. Like, okay, he says, be careful here. We can notice it from a different angle here, that you see there's actually, hold on, sorry. There's actually a pretty well marked yellow lane, but this old lane still kind of maybe distinct, but it comes here, right? And the autopilot kind of makes this bad perception. So this is probably this false positive and false negative event at the same time playing out, and it actually like changes the position of the car and making it dangerous, so that it's running into an obstacle that's just not acceptable. It's pretty dangerous. And we know like another accident happened maybe due to a similar cause, like I don't know that yet, where a person was killed in a different location, but again on the same highway. So this is something to watch out for, and sort of like be very aware of. It can happen.
So is it possible for the car, the AV, to be trained that they should just follow the higher contrast lane coloring and it's
Yes, like again, this example is that when we don't have a good, so like, you know, this type of situation was underrepresented in the training data. And basically, so what happens is that when, you know, the front camera sees this image, right? And it has low contrast, somehow it decides that, you know, that lane, the old lane, because I think what happens is that it was erased, but there's still sort of like this black kind of trail of old lane. It has a higher contrast, and then it sort of like switches to that, thinking that, oh, this is a real lane now, right? And makes it like extremely dangerous in this condition, right? So, but one thing to note here is that, again, this is a problem of a training data. So this type of situation need to be represented in a training data so that the lane detector actually knows that the real lane, it is like this low contrast, kind of hard to see in the camera view lane that, you know, we need to follow, not this old lane, and we need to ignore the old lane, otherwise it's pretty dangerous, right? And another thing here is that probably Tesla need to look at their camera processing and see, you know, if the contrast of those well-marked lane can be increased, so like a kind of solve the image quality problem that obviously exists in this front camera image. So let's look at the next slide. So again, this is something that I encountered in my work. And again, this relates to lane detection, and kind of, it's very simple to create this biased data set, because imagine that when you collect in the lane detector data set, your car will mostly go into the center of the lane, and you have, like, you know, the marking of the lanes on the side of the car. And then like, if you don't tell your driver to do, like, you know, pretty frequent lane changes, you're not going to get a lot of data when the lanes are positioned, you know, in some other kind of location, right? When, you know, you sort of like you in between the lanes and the actual lane in, like, maybe under your car, right? But that's still important to represent in the data set, because when you change lanes, like, again, let me show you this this location. This is also on 101, and this is a street view from Google, right? And you can see that. So you have the real lane, and then you come into this location. I think it's like a concrete insert on the highway, and then this old lanes markings, they were not erased. You know, they still exist. So basically what happens is that when, you know, we're going through this lane and we're doing a lane change, automatic lane change. So we come in between the real lanes, but then, you know, the old lanes come into existence. And then sort of like, because the data set is biased to think that, okay, I detect the lanes because I'm in the center and, you know, they to the sides of my car, you know, it starts to think, okay, oh, now this is a real lane. This is what, you know, I detected, the real lane. I ignore the other one because this is underrepresented. That situation is underrepresented in my data set. And essentially this just wreak havoc on your lane change procedure, because now it's sort of like you were changing lane, and then in the middle of it, you decide, oh, now I'm like driving in a real lane. So you start driving in this fake lane, and that's just not good, because you haven't finished your lane change, and maybe there are other cars around you that don't expect you to do this. So this obviously needs to be addressed. And the way how you solve this, you know, you need to collect data. You need to represent this this situation in your data set, so that, you know, when the lane change happens and the real lane becomes like, you know, the car becomes off-centered, it still knows that this is where the real lane is. You know, it doesn't start to think that you know, like, the old lane is my real lane. It actually ignores it, because basically, you know, when one thing to realize in the artificial intelligence, because when you train your detectors to recognize, to detect certain objects, you also train it to ignore other things. That's pretty important. That's maybe not super obvious. And, you know, when you train in this situation, your detector to recognize this lane as a real lane, you also train it to recognize these things as a fake lane and don't detect it as a real lane, because you haven't annotated it, and essentially that becomes sort of like a noise that needs to be ignored. It's dismissed in the inference time, and of course, like the way to achieve that is only by representing this situation in the training data. There's just no other way. I mean, you can try to maybe kind of create some sort of algorithm, but it's just not going to work really well. It's just going to fail. Like in another case, maybe it works in this case, but fails in another. So essentially, the solution here is to make sure that your data set is balanced and it represents all the type of situations that can be encountered in the real world, including this like old invalid lane markings, so that your lane detector works well in this in this situation.
So all this ML optimization in an industry setting outside of AV, right, is done by the product manager. So when AVs are still being built in the engineering realm, right? So
yeah, of course.
is that the engineer who's thinking of all these gaps and trying to figure out, do we get more training data? Is that where the reality of the industry is?
Well, I mean, I wouldn't think about it as just an engineering job. It's like a whole organization job. They need to be like a methodology built around how this type of problems are discovered, how the new data gets into into your training data sets, and how you sort of like you have this improvement loop. You have your autonomous vehicle going in the real world and encountering those challenging situations where it fails, and collecting the data. At the same time as you test, you need to collect this data, because when you discover this, you get this data and you add it to your training data set. And this is why, by the way, I think companies like Tesla has a tremendous advantage on the marketplace, because Tesla has a pretty large fleet. I think it's like maybe over 1 million cars right now, and those cars are constantly collecting data. Actually, what Tesla is doing is when you go charge to like a public charging, this supercharger network, right? So they have this huge supercharger network. The car will automatically connect to a Tesla network and download the data, or like upload some of the software changes that are used to this data collection. So essentially, Tesla is using its fleet, maybe even without drivers knowing, for kind of like bring back the data from the real world. And obviously, because of the scale, like of how many cars they have, they can collect all kind of data and sort of like consider all kind of situations. That's like a huge advantage that a car company like Tesla has, and others, because they don't have autonomous fleet yet on the road, at this scale, they will need to catch up. Okay, so let's conclude. I think we kind of pretty much well over time. And so modern AI is all about data. We saw that creating and managing data sets is expensive and time consuming, and it requires a very efficient and dedicated AI management platform. And then basically the way how companies approach this is that, this requires this cycle of encountering corner cases, or maybe like simulating them, and reiterating in your updates and data sets, retraining, revalidating. So this is sort of like this cycle that leads to improvement. And I guess the idea is that at some point, once you go through many iterations, you can declare that, okay, my AV is like very safe. The probability of it failing, like, extremely low, so that it's production ready, and it can be confidently released and shipped to the public.
Cool. Virend has a question about, when you say society, whose society? Is it going to be regulation or some consortium, or, or the owner of the car? It's definitely not owner of the car.
What's the question? I'm
So
sorry.
you said in corner cases, society has to decide what is the right way in that stop sign use case that you were giving.
Uh-huh.
Society has to decide. So he's asking who is society, right? In this case, is it
I mean,
company?
like that's not what I was commenting about. I was commenting about that's a sort of like open debate about I would like to call it sort of like a rule breaking dilemma, right? Um, we know that traffic rules they exist and we're supposed to follow them, but in reality, in most cases, we kind of like bend them a little as drivers, and that's just sort of like a reality of the world.
So it's like basically you're trying to programmatize the human judgment that we use on the road.
In a way, I mean, I'm not saying this should be done. I'm saying that there should be a debate in the society how this should be approached. There should be like something that's accepted by everybody. And example, I'll give you example. Like you have a speed limit, right, on the freeway 65, and you know that a police, traffic highway patrol will not stop you if you're going 5 miles over. Probably not. It's pretty unlikely. Although you're breaking the limit, you know that it's fine. So that's accepted. And again, we need to look at this, and we need to, as a society, as a kind of community of road users as drivers. We need to decide, how what would be the acceptable behavior, what would be the acceptable rules for autonomous vehicles. Should they also break, those laws a little bit, depending on, how people around are doing it? Or should they be very strictly law abiding? That's a big question. I don't know the answer to that. I mean, that's a debate. That's open for debate.
And Hani has a question that we should wrap up with that. Is there a business opportunity to create data sets and label them?
Of course, I think there is, yeah.
So that's what I keep saying. Data is what is where the power is. And I hope, the class got a feel for car cognition data. I love saying it as car cognition. I never say perception, because technically perception is literally perceiving the road, right? So
I think many companies are thinking about this sort of like a large scale data collection and labeling, and then kind of marketing those data sets as their business. And I can give you examples. Have you heard about this company called Nota? So they were like one of the first startups in this space, and they're actually not an autonomous vehicle company. So they're not developing AV technology, but they have a device that you can install. It's sort of like a kind of like a box that you install under your windshield, and basically that box will collect data and upload it to the cloud, and they can manage it. But their idea is that you take that box, you take that product, and you install it at a large fleet. Let's say it's I don't know, Uber network, or some sort of like a FedEx delivery vehicles. So like something, some cars that go out on the road as their business function, and basically they're just there anyway. And you can talk to them and say, okay, like just install this box, we'll give you some advantage, kind of, I don't know, monitor your fleet, or like offer some other kind of incentive, and then that will allow them to collect data from all those cars, and then like sell that data to other companies, let's say to AV development companies. So there's definitely a business opportunity here.
There's one of my student groups, projects that came out from class that continues on. One of them actually is working on something similar.
Okay, yeah.
Yeah, I can't talk about it yet. It's not public. Okay, this is fantastic.
So I hope it was useful. I tried to structure it in a good way, but yeah, there's a lot of information here, a lot of kind of different things. But I hope this was structured very well around challenge of data and
Yeah, this was good. And we actually have Alexander Varga. He co-teaches the Business of AV Data course with me, and he works at Volvo. And he actually was complimenting you when you were explaining the AI contextualization. So he was saying that's excellently done. So yeah, people are saying they like it. It's excellent. Great presentation. Thank you so much, Igor. This is awesome.
Okay.
Thank you for finding the time. And you're in the Slack group, right, of all my students.
Yeah. So Hani asked this question about the name of the company. I'm just reading the chat window right now. So what company?
You mentioned a startup just now.
Noto. Yeah, hold on. Let me type this.
Can you type that?
Yeah.
Okay.
Try to find. Yeah, they're like about maybe 3 years old, 4 years old. They were like one of the first kind of AV startups, or sort of like AV startups.
So it's a more perception-based company, right?
I mean, it's kind of interesting business model. I think they mostly focused about data collection and monitoring, right? So it's not exactly an AV company, but you can check their information. I included the link.
Okay. Okay, thank you. So with that, we should wrap up. This has been fantastic. Thank you so much. Yes, people love it.
Okay, I'm glad. I'm glad it's useful.
Yeah. Okay, awesome. Thank you so much, and hope other people can connect with you. Would you prefer if they talk to you on Slack or connect with you on LinkedIn?
LinkedIn is good. Yeah,
Okay.
I can connect on LinkedIn.
Sounds good. Awesome. Thank you so much.
Thank
Okay.
you.
Okay, bye.
Bye-bye.
Okay, bye, everybody. Thank you so much. Tahani, you are rocking it. I'm so glad you came. Okay, bye. I'm going to close out. Okay, bye.